Hey everyone, Thrasher here. We're introducing the idea of waves in this video. And because of that, we're going to look at the definition, the different types of waves that we're going to worry about, something called the wave speed equation, as well as interference. Hopefully though, based on maybe the level of math class you've taken, a lot of this is going to be review. So let's just dive right in. The first is, what are waves? And we have a physics definition. A wave is really just a disturbance. It's something that's transferring energy from one location to another. All right, it's energy going from position A to position B. And for the most part, waves are always going to be traveling through a material. We call that the medium in which the wave travels through. Sound waves, for example, are traveling through the air. Ocean waves travel through the water. There is an exception to this, even though we don't cover the topic. Light waves do not require a medium. Now, when we're discussing waves, you could make a single wave pulse, and that's really what this picture here is showing. We have a person holding a string that's tied to the wall right here. They move their hand up and down very quickly. That makes a single wave pulse, and we see it here as it's traveling to the right. Well, if the person kept moving their hands up and down, kind of like simple harmonic motion, you would get periodic waves. That's really just a bunch of these pulses happening over and over again. I'll again give you the example of ocean waves. You see those waves roll in time after time after time. They're very periodic. All right, they keep repeating over and over again. Waves, to reiterate, they're a transfer of energy. They are not moving matter. If I have a wave going from point A to point B, particles, matter, they are not going from A to B. There's a big difference between the motion of waves and the motion of particles. Particles actually, as we'll see soon, have a displacement overall of 0 as those waves are passing by. All right, so those are waves. Let's go to types of waves. Part B. Well, we have transverse waves. That's the first type that we're going to concern ourselves with. These are waves whose particles are disturbed perpendicular to the motion of the wave. This is a little unclear. Just reading that sentence doesn't give you a good sense of what that means. I have an animation to show you. All right, let me pull that up. Here I have a classic Phet simulator. All right, I can send single wave pulses. So here's a good example of a wave pulse that's passing through. If I go to oscillate, and I'm going to hit the slow motion button so we can see it clearly, these waves are being created over and over again, and they're moving to the right. Pretty clearly, they're moving to the right and out this window. The waves are moving to the right, but let's look at this green particle right here. That particle is not moving to the right. In fact, it's moving up and down. It's moving perpendicular. This is a transverse wave. It's not moving to the right like the wave is. It is instead moving perpendicular to that motion up and down. So that's what we mean by this definition. Examples, I just showed you a wave on a string. Light waves are transverse waves. Water waves often look like they're transverse waves, though technically ocean waves are kind of a combination of transverse and another type we'll see later on. When you think of a classic math wave or the sines or cosines graphs that you've drawn, those are transverse wave drawings. And there are a couple of terms we should know. The crest, that's the topmost part of the wave. The trough, T-R-O-U-G-H, funny word, T-R-O-U-G-H, trough, that's the bottommost part. Amplitude, we've seen this word before. It is still the distance from this line, which we will sometimes call the equilibrium position, kind of the x-axis from like math class, to the top, that's amplitude. You could also draw the amplitude from the top down. In this class, we're really not going to see waves that have drastically changing amplitudes, at least not in any kind of problem where you'll need to know the amplitude. Last thing, wavelength. This is a term you may have seen before in other classes, but we have not talked about in in physics class. Wavelength is the distance between two successive points. Distance between two, and when I say successive, I mean identical. The same kind of spot on this repeating motion. Distance between identical points. What they've drawn here is the classic way. We have a crest, we have a crest. The distance from one crest to the next, that's the wavelength. But that's not the only way you could draw a wavelength. From here to here, trough to trough. This is also a wavelength. You could even do, let me change my pen color one more time. I could go like right here, where the wave is about to dip down, to the next point where it's about to dip down. This is also a wavelength. All right, this symbol right here, lowercase Greek letter lambda, that represents wavelength. It's measured in meters. It's a distance, m. And this is good. So that way when we're talking about the size or the length of waves, we always know what we're talking about because these waves can go on forever. All right, wavelength is the way that we can measure them. Okay? There is one more term we really should know, and that's the period of a wave. If wavelength is how long a wave is, period is the time it takes for one wavelength to pass a given point. It's given the letter T, uppercase T, for period. We've seen this symbol before, and again, it's measured in seconds, SEC. So we also have periods for waves. It's the time it takes for one wavelength. That's kind of like our time for one cycle that we saw in simple harmonic motion. All right, that is our first type of wave, transverse. There's another type known as longitudinal waves. These are waves whose particles are disturbed parallel to their motion. Sound is a classic example, and some earthquakes are examples. Let's see a visual of longitudinal waves. They're kind of trippy at first. These are longitudinal. Let's look. Let me switch to my mouse here. Let's look right here. We see this wave sliding to the right. In both of these visuals, the waves are moving to the right. But look at this, they're highlighting a particle. This particle is not continuing to slide to the right. It's moving back and forth. In fact, you could pick any of these particles. Let's look at this one. Back and forth. The particles are moving parallel. The wave is moving to the right. The particles are moving parallel to the left and to the right. All right. For these longitudinal waves, you might see this term compression and rarefaction. Compression is where the waves are all bunched up and close together. Rarefaction is where they're all loose. They're more separated. So here we have compression, right, like this, compression. Here we have rarefaction. Compression right here, rarefaction right here. The wavelength is really the same thing. It's the distance from like rarefaction to rarefaction, two successive points, or from compression to compression. We are not, however, going to really worry about like the amplitude of longitudinal waves. Okay, so those are our two types of waves, longitudinal. Next is the wave speed equation. We just saw a couple diagrams, and we could probably figure that those waves seem to be moving with a certain speed. How could we calculate the speed of these waves? Well, if I go back to my basic definition, speed is delta x over delta t. So we should be able to use this for a wave. I just need to know what the change in x is and what the change in t is. And for waves, the x, that horizontal distance, that's wavelength. And the time for one wavelength to pass, that's period. So one form of the wave speed equation, it's wavelength divided by period. So I can figure out the speed of these waves by taking the wavelength of that wave, dividing it by the period, the time it takes for one of those wavelengths to pass. However, there is a slightly more common equation, and it comes from this relationship. Remember that period, t, and frequency f, they're inverses. They're kind of opposites of one another. So I could plug this into right here, which means if I wrote it out again, I have v equals lambda over, instead of t, I'm going to grab my blue and write 1 over f. Because if f is 1 over t, t is equal to 1 over f. So I plug that in right there. And if I am dividing by 1 over something, that means I can bring this to the top. And what I get is v equals f lambda. This is the classic wave speed equation. This is the one that is on the equation sheet. It's not to say this one's wrong. They're both valid, but this one is more common. So the speed is based on the frequency of the wave multiplied by the wavelength. The units for speed are still going to be meters per second. That's not changing. All right, that's wave speed. We only have one more thing to go over, and that's interference, sometimes called the law of superposition. That's a fancy word, or a fancy string of words, law of superposition, just meaning interference. First, remember, waves are not matter. They're energy going from one location to another. There's a classic rule in science that says matter, things with mass, can't occupy the same space at the same time. You have your table, and you have maybe a coffee cup that's sitting on the table. Well, those are two things, and they're occupying different places. The table is occupying the place where the table is. The coffee cup is right above it. You can't put the coffee cup in the same spot, literally the exact same spot at the same time as the table. Okay? It doesn't work out. You might even like saw a hole in the table so you could like wedge the coffee cup in there, but you can't have two things occupying the same space, two things with matter. But that rule, that requirement is not true about waves, because waves do not have mass. They are not matter. So therefore, you can have waves occupying the same space. And when they do, they interact. And the way those waves interact when they're occupying the same space at the same time is known as interference. And there's two ways. The first is constructive interference. Let's look at two wave pulses that are on the same side. So we have A and we have B. Their amplitudes are both up. Remember, you could have an amplitude up or you could have an amplitude that's down. But let's just look at the case where two amplitudes are on the same side. They're both upwards. And I kind of like to look at this as adding numbers. If they're both up, they're both on the top, maybe you consider these like little positive numbers, +1 and +1. I'm just making this up. When you have pulses, amplitudes that are on the same side, when they meet, when they join together, sorry, I can't make a straight line, they add up. If I have an upward amplitude and an upward amplitude, they make a larger upward amplitude. It's like adding positive numbers, +1 and +1. That looks like you get +2. But there's an important thing to recognize. Those wave pulses are really still there. Like wave pulse A is still existing right here. It still has some energy. It's still moving. Wave pulse B, which unfortunately they drew as the same color, but wave pulse B is still there. Wave pulse B is still moving this way. Wave pulse A is still moving to the right. Just the result, we see them interacting in a way that's building, constructing. Also, after this interference, they keep going the way they were. They're not destroyed. They're not obliterated. They keep on moving. This does not have any overall effect on these wave pulses. They're not permanently damaged or anything. Let me go to another visual showing us superposition. Here again, we have constructive interference. We're going to have a tall wave on the left, a smaller wave on the right, but when they meet, they, interfere. What we see is the thick, solid black lines, but I like this visual because they also have that blue and the red line showing that those two wave pulses are still there. See, right there. And they keep moving after. They're not destroyed, nothing like that. All right, so that's constructive interference. Last thing is destructive. It's kind of the opposite. If you have wave pulses that are on opposite sides, if I have one like this and one like this, or if I have one like this and one like this, if they're on opposite sides, when they meet up, they cancel. It's like having +1, and since this is kind of the same size, this is like -1. Well, what's +1 and -1? You get about 0 right here. So it looks like there's no wave at all for a moment until those waves keep moving. By the way, they don't have to be the same size. I could have one very positive and one slightly negative. And if this one's moving like this one's moving like this. If we assume the widths are the same, maybe what you get is just a slightly less positive. Because that -1 is still in there. Sorry, I'm not very good at drawing. So it canceled a little bit of this. But +3 plus -1, I'm still left with an overall +2. Again, I like using those numbers. Again, I can go back to my visual here. If I scroll down a little bit, this is showing them with the same amplitude, but we can see here are our two waves. And this bottom part is imagining they're overlapping. Let's look right here. When I have crest and crest, that's constructive interference, I get a big crest. But when it's crest and trough, that's destructive, and the wave cancels out. So we see times when you have constructive interference, like right here and right here. And by the way, it can have constructive interference when they're both negative. Look at this. -1 and -1 is -2. They also add when they're opposite. But again, when they are opposite on the two different waves, if I have a positive amplitude and a negative, they cancel out. That's destructive interference. Okay? Again, make sure you recognize those waves aren't being permanently destroyed or altered. Once they pass by, they pass by. They keep moving the way they were. Okay, that's it. That was a lot of information going over waves, the wave speed equation, the types of waves, and interference. Thanks for watching.